Today we will talk about depth first search, shortly DFS, it's a similar algorithm as breadth first search, but it has other idea in center of it. So we'll start with, of course, definitions. Today we will talk about trees and forests. As I think you know, tree is connected graph without cycles, and the forest is a union of trees. Okay, it's simple. Yeah, nice. So about depth of first search, about idea of it, if we remember BFS, yeah, it like waves on the water. Remember it? And DFS has as idea, it like a thunderbolt that start in one vertex and go down to the deepest side of the graph. Okay. So about algorithm. Firstly, we will start in one point and follow the edges while we can get new unexplored vertex that are adjacent to the last. Okay, and when we end first step, yeah, for example, in this vertex, we can say that there are no any adjacent vertices that are unexplored. Okay. So when we say this, we go to the second step of this algorithm and back to the last point that have any adjacent unexplored vertices and recursively explore them. Okay. And if we end first three steps and we have any unexplored vertices in the graph, so we say that, for example, if it is undirected graph, we say that this graph have some connected components and then repeat this algorithm for other component. Okay. So it's about implementation. Go to the example. Yeah, and there are coverings and two important numbers that we have to each vertices in the end of the algorithm. Okay. And each algorithm have time that we explore it and time when we finish to explore adjacent vertices of this vertex. So, for example, about pseudocode of the algorithm, we can see that at the start of the our algorithm, our graph had all vertices like white vertices that have no any times as we see on this graph. Okay. Then we start with one vertex and say that it has time or explore time equal to 1. Yep. Then we visit this point. Okay. Then we set time to this point and see do we have any adjacent vertices to U vertex? that haven't been explored. Okay, and if we have these adjacent vertices, so we visit them too. Okay, and then repeat this cycle while we have any adjacent unexplored vertices. And if we have explored all adjacent vertices, we say, okay, we finish this vertex and say that it's time then we finish explore this vertex. Okay. So about example, we start with the point A. Then we see that there are one adjacent vertex B that is unexplored. Yeah, and go to this vertex. Okay, and say that time 2, it's time when we explore vertex B. Okay. Any questions? No. It's simple. Very. Okay. Then we repeat algorithm for B, repeat for E, for C. Then we see that F has no any adjacent vertices, so we finish to explore it and go back to the vertex E. Yeah, and we see that vertex E have different adjacent vertex that have now been explored. So we go to the vertex D, we visit it, and see that vertex D has only one adjacent vertex A, and it has been explored. So, yeah, we finish with vertex D. We say that each vertex has only one adjacent vertex and it has explored. So we finish with D, we finish with E, we finish with B, and we finish with A. Yeah, and we see there are no any other unexplored vertices, so we have only one connected component. We see that there are no other unexplored vertices, so we say that graph has only one connected component. Okay, but if you see, for example, this graph is directed. So when we say that it has only one connected component, we see that, for example, from F to B, we has no path through the edges, yeah, because of the direction. But, for example, if we start with vertex F defense, we see that only one vertex can be reachable from this vertex. Yeah, and then when we repeat algorithm for vertices A, for example, B, E, D, we see that, for example, from B we can reach F and we connect this graph. Okay. So of course we are lucky that when we start with vertex A, we can reach all vertices in the graph. But if we start with F, for example, yeah, we can transform our algorithm and see, of course, all these connected components. Okay.
But
yeah.
a connected component is a component in which you can reach any other points from them.
Yep. Now I say about small connected component. It defines as you can erase directions of the edges, and then see which vertices can be reachable from each other.
So the definition, for example, the definition we have for connected components when the graph is directed.
Okay, we have two different definitions, and for the second definition we will talk because of other algorithm that we will talk in 10 minutes,
Okay.
I think. Okay. So now you can see, for example, for this graph, that if we erase directions, yep, it will be a connected connected components, and it's one of the definition of connectedness of the directed graph. And about strongly connected component we will say in some minutes. Okay. And for example, in this graph we have three strongly connected components: 1, 2, and 3. But of course we will talk about it not now. So, yep. About time and space complexity, as we can say, as for breadth first search, yeah. Remember that breadth first search has time complexity equal to O from number of vertices and number of edges. Remember it? Nice. And so for DFS we have the similar results. Do you understand why it is true? Why it is true? Why we have this time complexity and this space complexity?
For the first one, because we will go to every node and we also explore
Yeah, yep. Yeah.
edges.
Yeah, because as you can see, when we go, for example, to node D, we of course search all of incidents edges to this point. Yep. And then we go to the any vertices. So we have v number here, and we need to visit all edges from the start point of this edge, and so we have this number here too. Okay. And about time complexity. Yeah, yeah. Because of times.
Yeah, because we know how to write which nodes we already visit.
Yeah, yeah, of course. But if you can see here, we have big node class, yep, with color, with parents, with final time, and so with discover time. So we can do big class node and have no other arrays in the algorithm, because we store it in this node. Okay. But of course, there are any other implementations of DFS, and you can use other, not this. Okay. So about trees and edges, yeah, we can see here we have DFS tree. Yep. It has black edges, and we have edges in the graph that are not in the tree DFS. Okay, so there is classification of edges. Yep.
Why do we use for now? Is it the same as with 0 and 1?
Why we use colors? Okay, we need to understand which vertices we have already explored. So if you use, for example, a bool variable to this, it's equal to this coloring. So if we have no stored this information, as you can see, we can cycle our algorithm, yep, because we go to the D vertex and then say, oh, okay, it has adjacent vertex A, and we go to A. And then we have infinite cycle in our algorithm, okay? So, oh, I can see chat now. Nice. So to stop our algorithm and not to visit vertices that we have explored, we need to store this information in the node. Okay. Now, can you move it to the right? Yeah, nice. Yeah, I see it now. Oh no. Yep, nice. Yep. Oh, okay. Why do we and could you explain what is time in the pseudocode? What is the time in pseudocode? You can think that time is equal to time in the real, but we store it as a variable because we need to understand in which order we visit each vertices. Because we have different applications of this algorithm, and so we need these times, and we say in some minutes why it is good to store time when we explore vertex and time when we finish to explore it. Okay. And do you have any questions? No? All is understandable. Nice. And about classification of edges. We can see this picture. There are black edges that includes to DFS tree, and there are three types other edges. For example, red edges name as back edges that have a start point in the vertex A and endpoint in the vertex that is ancestor of vertex A. Okay, and formal definition here. Yep, that H O to V names as back edge if V is ancestor to vertex O. Okay. So if there are other direction of this edge, for example, we see that if it is vertex O and this is vertex V, we say that O is an ancestor to the vertex V. Yep. So we say that it is forward edge. And so we have cross edges that connect that connects vertices that has no order in this tree. Okay. So it's about forward edges. We say that edge that starts in vertex U and ends in vertex V, that is, it is forward edge if U is an ancestor to vertex V. As we see in the tree, U have the path to the vertex V.
Okay.
Yep. So, about applications of DFS. Yep, there are different applications in the real tasks, for example, solving mazes, and for example, job scheduling. And of course, it has different applications in exercises that appear in graph algorithms, and we see next on the next slides that DFS is useful in this direction. Okay. So about first task and solution with the DFS. For example, if we have directed graph and we want to find a cycle in this directed graph, and of course we say that path names as cycle if every edge has directed from vertex E to vertex E plus 1. Yep. If, for example, we reverse this edge, it will not be cycle. Okay. So there are we want to find directed cycles. Okay. How DFS is used in job scheduling? Could you please explain shortly? Okay. Okay. I will write some example here about job scheduling. For example, if you have different tasks in your job, yep, and one task depends on other task. For example, to start the lecture, I need to create a presentation, for example. And so we write it like an directed edge from 1 to 2 vertex. Okay? And so we write dependencies of the tasks. Yep. For example, and of course, we try to avoid these cases because of we cannot solve cycle tasks without do it in the same time. Yep. So we think that this graph has no directed cycles. And then we can order these tasks like this, for example. 2, 4, 6, 5. In this order, because if we do task A and so task 3, we can do task 2. Yep. And we can, for example, do this task in this order. This is about job scheduling. Is it understandable? And for you too?
Yeah.
Nice. And I'll go to the slides. It's about cycle detection and about ideas that we see in the job scheduling. We can see if we have directed cycle graph that is shortly named names as DAG. Yep, as DFS, as BFS. We'll use a short abbreviation of this sentence. And then we will see this graph has no directed cycles. Yep. And we want to represent this graph as tasks on the other board when we use it to schedule our job tasks. And solution of this task names as the topological sort.
Well, directed untitled graph.
Directed acyclic graph. Yep. Of course, we have cycles that have edges in the both directions, but we have no cycles like this. Yep, that have edges in the same direction. Understandable? Yep. So, for example, we can use DFS and induce from this numeration of our graph. And for example, if you say to me different numbers from 1 to 15, say some, or say some edges that we have in the graph. B, from B to N, for example, yep. And we see that B have 8 number and N has 13 number, yep. And if you see on this figure, you can see that any edge that starts in vertex V and ends in vertex U, it has number of vertex V smaller than number of vertex U. For example, there is edge F to R, and F has 4 number, and R has 5 number. Yep. And for any edges in this graph, there is condition that is completed in this numeration. Okay. And about pseudocode of topological sorts, it likes DFS. It very it's very similar to DFS, but we can see that we have list L that stores numeration of vertices that we explored. So when we finish with vertex U, for example, we push it to the list L. Yep. So numeration of the graph that we have and order that we set our vertices equal to post order of or reverse order of finish times of the vertices. You can see. For example, here we have directed graph. Yep. And we start the phase from one vertex. For example, from E. And we go to the B, go to the D, finish with it, explore E, and other steps of the phase. Yep. And then we see, for example, when we end with D, it is first vertex that we finished with it. Yep. We push it into the list, and it has the smallest order in our numeration. So then we go to the B, go to the adjacent vertex that have no explorers, and finish with it, and push it to the list. Yep. So then we finish with vertex V, vertex B, and push it to the list. Then we go to the F, go to the G, and finish with G. Oh, no. We go to the C vertex and finish with it. And then go to the G, finish with it, then finish with F vertex, and then finish with A vertex. So it is this numeration is equal to the order that we get from the finish time of each vertices. Okay? Understandable?
Yeah.
Right.
Number 3.
Number 3 in this example. The last. Yeah.
How would we get it?
Or in this list. How we get it is in this list. Okay. So let's to understand where we start this diffuse algorithm. For example, we will start from 3. Yep. But let's me to talk about if we start with 3, and so then I tell you points where we reach one vertex. If we start with 3, I use different. Oh, no other colors. Yep. Yes. No. Here. Oh, yes. Nice. For example, if we start with 3, we go to the 2 vertex, then we go to this vertex, and go to this vertex. Then we finish with 5. It's time to add it in the list. Then we finish with 6, and we add to the list. Then we finish, we go to the 4, and then finish with it, and push it to the list. Then we finish with 2. Yep. And we finish with 3. Okay.
3 to 2 is not connected.
2 is not connected to 3, but 3 is the parents of the 2. And when we finish with 2, we say that 3 has no other adjacent unexplored vertices, then if we see in the algorithm, if there exist unexplored vertices, repeat the algorithm for them. Yep. And we see in the pseudocode that function dfs repeat for each vertex our algorithm. And we tree that we have on the left board equal to result of the dfs visit function. And then function dfs try to understand each vertex has black color or no, and it finds that one has white color and starts dfs visit from this vertex too. And then our algorithm says that it new vertex that we start our dfs, and then we have no adjacent unexplored vertices, so we end it and push it to the list. Understandable? Nice. Sorry, still I don't understand the logic for time in dfs. Masoud, do you understand about discover time and finish time? About when we start to explore vertex, we say that it is time when we discover and set discover time to the time that we have. Then, when we finish to explore all adjacent vertices to the vertex U, we say that it's time when we finish with vertex U and set that is time that finish time is equal to time that we have. And I can make other example of dfs, for example. Masoud, can you tell, do you need any other example? Oh. So, it's bad. I think, okay, I'll explain, repeat to explain, okay. So, time is equal to, for example, real time. So we say that U point D is equal to time when we discover our vertex U, and U point F is equal to time when we finish to exploring adjacent vertices. So in the end of dfs, each vertex has two times when we start to explore it and when we finish to explore this vertex and adjacent to it. Oh, see, nice. So, about topological sort, it was example, okay, and we have other time too. Okay, about other tasks that can be solvable with dfs. it's about a strongly connected component. It is other definition of connectedness in the directed graph. Okay, and as you can see on this figure, there are four parts of our graph that contains vertices that are reachable from each other. Yeah, as you can see, for example, if it is A vertex, if it is B vertex, then we have path from A to B, directed path, of course, and we have directed graph, directed path from B to A. And for example, if we get vertices from different strongly connected components, for example, if it is A vertex and it is B vertex, then there are two cases. For example, as you can see, there is path from A to B, yep, that and there is no path from B to A. But of course, if you say, for example, that it is vertex A and it is vertex B, there are no any paths in both directions. No path from A to B and no path from B to A. So we can say that it is strongly connected component, and this is other strongly connected component if two conditions are completed. Yep, condition that two vertices in connected component have two paths from 1 to B and from B to A. Yep, and that I said about vertices from the different components. Okay, it's about the definition of strongly connected component. So about finding this connected component, as we can see on the previous slide, if we draw each connected component as one vertex, so we see directed acyclic graph. And so if we start, for example, in one vertex in a green connected component and go down to the other vertices as in the depth first search. Yep, we go to the point that has no other adjacent vertices that are unexplored, and in this time we say that it is this vertex has connected components that has no edges from these components to other components. I repeat it. First vertex that we finish with it contains in connected component that has no edges like this, that starts in this connected component and ends in other strongly connected components. So, for example,
if there was like this, it
Mhm.
would be a strongly connected component.
Yep. Yeah. Of course, if we have, for example, edge from this component to this, we have one strong component, but not the three. Okay, and other viewing of this figure that, for example, if we end in vertex in this connected component, and if we reverse all edges in this graph, then there is no edges that starts in this component and go to the other strongly connected component. It's simple too. If we reverse all edges, of course. So, about algorithm that solves this task. Okay. First step is simple. It's only DFS. But then, in the second step, we reverse all directions, and then we start DFS from the last point, from the last vertex that we visit in the DFS. And all vertices that we can reach in new graph with reversible edges, these vertices will be in the strong connected component of vertex that we visit last. And then we repeat this algorithm to each for each vertices that we don't visit in the DFS visit. So, for example, if we have our graph that we saw a few moments earlier, so we can start DFS from I forget. Yep, we start with this vertex. If we start DFS from this vertex, then we go to this vertex, then we finish with it, 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 and numbers on this vertices are equal to finish time of our DFS. Okay, I can draw discover time, but it isn't important to work of this algorithm. We need to store only finish time of vertices. Okay? So then, when we have graph with nodes that store finish time of DFS, then we reverse all edges and repeat DFS visit function DFS visit from vertex that has the biggest number. Okay, then we start with vertex 32. Yep, and as you can see in the last figure, there are only 5 vertices that we can reach from this vertex in new graph, and all of these vertices will be contained in strongly connected component of vertex 32. Okay, then when we end DFS visit, we see that we visit these vertices, and we have 30 like the biggest number in other component of graph that we don't visit earlier. So we repeat our algorithm to this vertex, but of course we cannot explore vertices that we explored before it. For example, we see that this orange vertex was explored before this, and it contains in these strongly connected components. So we see that and these two. So we say that this yellow vertex has no adjacent vertices in a reversible graph. So it makes a small, strongly connected component. Okay, and when we say it, we repeat our diffuse visit for the next biggest number, for example, 29. Yeah, and we see that there are paths from 29 to 24 or to 28, 27 and 26. So it is other strongly connected component. When we finish with red, yellow and orange connected components, we see that in the other parts of the graph we have 14 as the biggest number. And so we start diffuse visit from this vertex and we visit two vertices. Then when we end it, we see that in the last part of the graph we have 12 the biggest number, and we make last step of diffuse visit and so see that in the last strongly connected component of our graph. Okay, and so I think I can make other example about. Oh yeah.
We start, for example, if we start from 32, then that.
Oh, please repeat.
32.
Yeah.
Yes. We went to 31.
Yep.
And then after that, 30, 29,
30.
30 and 29. We explored this part. And then we went back to
No. In the firstly, I write times equal to finish times of each vertex. And diffuse that we start in 32 has no path like this. It starts with 32, 31, then 14, 13, 12, 11, 8, and 8 it is first vertex that we finish with it. I repeat it with the example. Okay, and other example, for example, okay. For example, we have this graph initially, and we will start with, for example, this vertex. We open it, then we see that this is unexplored vertex adjacent to it. Then we see this adjacent this, this, and this. And we see this vertex has only one adjacent, but it is explored. Yep, so we finish with it. We go to this, finish with this, finish with this, etc. Okay, then we store only finish time, and I erase time when we discover these vertices. Okay, and this these numbers equal to numbers that I draw in the figure on the slides. Okay. This 8 number. Why? Because when we start with this vertex, it was first time, second, third, fourth, fifth, sixth, seventh, and we finish with it in the one time plus in the 8 time. Understandable? Or?
Yeah, like then how big it is?
How 11. Okay, when we finish with it, vertex, it was 8 number. Then I go back to the pictures and go to this and open and finish it. Finish with number 10. And then I finish with this vertex with number 11. Okay. I try to put it in vertices. Then, what is the second step of the algorithm? Reverse all edges. Yeah. So I need to erase direction and set other direction for this. So I use other color to get quicker this. And erase. No, to avoid any conflicts with understanding of this graph. Okay. It's the graph with reverse edges. Yep. Then we see, okay, we have 16 as the biggest number of these vertices. And then we start from these points our first strongly connected component in the graph. And we go to the 14, go to the 15, and say, oh, there are no any adjacent vertices, and our first strongly connected component. For example, we can go back and see that there is no any adjacent as defense. Then we see we can forget this part of the graph and see there is 13 is the biggest number of part that we haven't get in the first step. So we start second defense visit from this vertex and see, okay, we have only one adjacent vertex, but it has already explored in the first step. Yep. So it is new strongly connected component. Then we see that 12 is the biggest number. And we start defense visit from this. We go to 10, 11, go to 8, and that's all. Yep. It's the last strongly connected component. We end with finding strongly connected components. We talked about topological sorts, and now we talk about other tasks that can be solvable with algorithms that names as Ford-Fulkerson algorithm, and it contains, of course, BFS and DFS in it. So let's start to talk about it. There is other class of graphs that we need to explore. I can draw example of flow network to understand definitions. For example, if we have some vertices, we can represent them in the plane that, for example, each edge starts with one vertex, go to the other, like other directed graph. And of course, graph can have directed cycles, for example. Okay, and as you can see on the slides, there are two distinguished vertices, source and sink. And we say by definition that source has no input edges and sink has no output edges. Okay, and here we can draw any directed graph. Then second important point of this class of graph is that each edge has capacity. It is function from edges to real numbers bigger to 0 or equal to it. It's any different functions, but of course we say that algorithm for Ford-Fulkerson algorithm works with only integer capacities. Okay, and for example, I can draw capacities of this graph. For example, 5, 4, 3, 2, and of course we can have edges in both directions, and they can have different capacities. For example, it can occur in our graph. And okay, and this graph can be named as flow network. But of course, we need to understand what is flow, and you can see definition of it. Yep, it's similar to capacity. It is to function from set of edges to the real numbers that bigger than 0 or equal to it. But there are 3 conditions that we need to be met. First, very important, that flow cannot be bigger than capacity of edge. It's understandable. For example, you can try to understand flow network as a transport network or flow network in the houses that we have. Yep. Or for example, you can represent the vertices as cities and edges like roads between cities, and you have constraints with constraints of the roads of your country, for example. Yep. So it is understandable that flow can be bigger than capacity, and we say that every edge has a flow in one direction equal to minus flow in other direction, and of course we think about it like our graph has edges between any 2 vertices, but if we don't draw edge, then we say that this edge has capacity equal to 0. Okay? So if, for example, we can say that there is no edge between source and sink, so this edge has 0 capacity. Okay? And for example, we can say that capacity of the edge BA is equal to 0. Okay? Because we don't draw it. So, and the last condition is equal that we have no troubles in the vertices because of conversation of flow. Yeah, we say that if we has flow, we can sum all flows that input in vertex and sum of all output flow, and it must be equal. Understandable? Yeah. And for example, I can draw some flow. For example, to no. 1. It's equal to 1, 2. 2. Then, for example, 2. 1. 1. 2. 1. 1. 1. 1. 1. Oh no, we need to. Okay. Red numbers is equal to flow of the edges. I can write.
The black numbers is just random number
No, it is capacities of the edges. Numbers are flow of you get a flow network initially, and flow network has capacities of each edges. You don't need to understand what is the capacity of the edge. You get it like all of the graph. Yeah. It contains in input of the data. Oh.
The flow will be
Here?
that, yes.
Yep. And what?
The flow for will be
Oh.
there is variable like the
Do we need to get flow in the other direction?
I mean the flow will be -2.
Here? No. Flow is equal. Flow is the function of the edge. And we can say that, for example, I need to name this vertices. For example, it's B and D. We can say that edge CD has flow equal to 2, and edge DC has no flow, or flow is equal to 0. Oh, okay, about, yeah, you're right. We can say that it's equal to -2, 2. Yeah. So, and black numbers is equal to capacities, okay? And so we can say that if we sum flow of the edges that out from the source, it's equal to 3, and it is value of a flow. Okay? We say that value of flow is the sum of the flow derived from the source. Or for example, or conversation. Oh, for example, you can see if we
What is E?
E is the
Yep. For example, for D, we say that sum of flows that starts in D and ends in V. For example, here we can say that this edge has capacity equal to 0, and so flow equal to -2. So if we sum all of the edges incident on vertex D, it will be equal to 0.
Yeah.
But of course, if we see about this source or sink, yeah. Okay. So about Ford-Fulkerson algorithm. Oh, it's very big network to use it, I think. But I can draw one thing that says that this flow is the maximal flow in this network. You can see that if we cut our graph in two parts, this and this part, there are two edges between them, and sum of the capacities of these edges equal to 3. And our flow has value equal to 3 too. So I can say that this cut names as minimal cut of the network, and our flow names as maximal flow. And there is a theorem I can write it that in the any flow network, minimal cut is equal, capacity of minimal cut is equal to value of the maximal flow. Any flow. Any flow network maximal of values of flows is equal to capacity of the minimal and I will say about it in some minutes too. But now we can see that if we have flow in the network and have capacities, we can draw other network names as a residual network that can be built by the algorithm. And I get other example to this. For example, if we have this network with capacities equal to 1. Firstly, and you can see on the sides, so first step, we say that flow is equal to 0. Then we build residual network. We get no. Oh, and can I copy it? Do you know how to copy this? No. Hmm? Where?
The fourth one, yes.
Fourth?
Maybe
No, no, no.
the top of this one. Yeah, if you watch again. Or
Maybe next
next to the color. Yeah.
Oh. Nope. Okay, I will draw it. Okay. And in the residual network, we say that there are edges, there are forward and backward edges. And I now say how to compute it. For example, about forward edges, we have for each edge capacity of this edge, and we have flow that go through this edge. And capacity minus flow is equal to the number that I need to write on the edge. For example, it's equal to 1. So, and equals 1, 2. Okay. And in the other direction, I need to do the same, but of course, I say that capacity of these edges equal to 0. Yeah. So I write these numbers of edges and this too. And I say that it is capacities of edges in the new graph that we name as a residual network. Okay. So I try to find a path from the source to sink. For example, I can draw and find this path. And if we have an augmenting path, we say that this flow isn't the maximal flow of the graph. Then we say that we can increase our flow at this path in the flow. And then we get new flow in our network. We draw our graph with capacities. And we increase our flow. Yep. Value of this now is equal to 1. It's bigger than value of this flow. Okay. And now it is important that we have the augmenting path in the residual network for this flow. You can see that if I draw it, we have all of the edges. And as I said earlier, that we have these capacities of these edges, and for example, for this we have 0, for this we have 0, for this we have 1, 1, and 0, 2. Yep. But we have backward edges, and now we have 3 edges with capacities equal to 1. This backward edge has capacity equal to 1. This, and this has capacity equal to 0. Okay, and now we see that we have path from the source to the sink through these edges. And we can use backward edges too. And if we use backward edges, it means that we need to decrease flow through this edge. And now we can draw new new network. We have the same capacities. And now we have flow that has value equal to 2. Yeah? We can see that we increase value of the flow. And if we try to draw residual network, and write all the capacities. Yep. For example, 0, 0, 0, 0, 1. Oh, no. 0, 1, 0, 0, and backwards edges, it's equal to 1, 1, 0, 1, and 1. And of course, if there are no capacities on the edges, we can say that we have the path from the source to the sink, yeah? But we need to get edges with non-zero capacities in the path. So we say that there is no paths from the source to sink that contains only edges with capacities bigger than zero. So we can try to find where which vertices we can reach with spaces contains only edges bigger than zero, and we say that there are no one vertices that we can reach from the source. So it is minimal cut of the network. And it is 3 steps of the algorithm names as Ford-Fulkerson algorithm. And for example, it is proof of the theorem that I write here. Because when we get the maximal flow in the residual network, we can get minimal cut of the network capacity of it equal to maximal float. Okay, but there are 2 problems with this algorithm. Go to the slides and about time complexity. Of course, we can use DFS or BFS that we researched earlier to find augmenting path. And we spent only O from number of edges time to find the path from the source to the sink. But we can draw an example when time complexity of this algorithm is equal to number of edges multiplied by maximal of capacities of the edges. For example, if we can draw the similar graph, but the capacity the capacities of 4 of these edges will be equal to 1000, for example. And this capacity equal to 1. Then we can try to use a Ford-Fulkerson algorithm, and in each step we increase our flow only by 1. And then we get 2000 steps of the algorithm. Yeah, it is of course of the big capacity of the edges. Okay? And I can... Do you understand this?
No.
Nope?
No.
Why it is equal to 2000 steps? Okay, go back to this example. We can get augmenting path through the middle edge in each step. And then we say that we can increase only by 1, because my minimal capacities of edges that contain in paths that go through the middle edge is equal to 1. So if we increase our flow with the augmenting path that go through the middle edge, we can increase only by 1. Of course, if we get this augmenting path, we increase our flow by 1000, then increase by 1000, and we have 2 steps. Yeah. But if we have a random random choice of the augmenting path, we can, for example, choose in each step paths that go through the middle edge. And then when we get two steps and increase flow that go through the upper path and go to through the lower space path by 1 because of this two steps or 3 steps of the algorithm. And then we get flow equal to 2, or then we get 2 steps of the algorithm. Then we repeat this, and we get flow that will be equal to 4, then will be equal to 6, etc. I need to repeat it too. Yep. No? Okay.
Augmented path, and what is
Augmented path is the path in the residual network that contains only edges with capacities bigger than 0 that start in the source and ends in the sink. Residual network, if we have flow network with flow, we say that residual network is equal by vertices to the flow network, and each edge has capacity equal to this. It is the new capacity of the edge E in residual network. So we see flow is equal to 0, so capacities of the edges equal to capacities in this network. But on the second step, we see we have not 0 flow, and say that, for example, for edge that connect these two vertices will be equal to 0, because it is the difference between capacity and flow. Understandable? So, for example, if we try to understand it, yeah, we get augmenting path, and initially we have 0 flow. Then in one step we get flow that will be equal to 1. as in the previous example. Then we increase by increasing flow through this edge, and decrease flow through this edge. And we get new flow value of this flow is equal to 2, but of course we need to repeat the steps 2000 times to increase flow to 2000. Do I need to make next two steps of this algorithm? No? Better to draw it. No? Who understands it? You? Other? Understand? Okay, and questions? Can you make a question about this? Do I understand fourth-Parker's algorithm? Nope. I need to repeat it. I need to repeat. Okay, do you understand what is the flow network?
Yeah. Definition, yes.
This is the definition of flow network. We have direct graph with capacitors. And we have two distinguished processes, source and sink. Okay. Then, do you understand what is the flow?
Yes.
Understand. I draw it like red numbers of the edges. So, then if we have flow network with flow, we can draw residual network by the algorithm. Yep. We need to make a residual network and find the augmenting path. How we can draw this residual network? We draw vertices like in the initial graph. And then we say that edge in the residual network has capacity equal to difference between capacity of this edge and flow. It is understandable too. And okay, we build residual network. Then we try to find path in this residual network from the source to sink that contains only edges with capacities bigger than 0. For example, in this picture we have these 3 edges that connect source and sink and has capacities bigger than 0. So we say that we can increase our flow using this path, and to increase edges flow on these edges, on this.
Okay.
You can see
Yeah.
by the augmenting path.
Yes.
Then we repeat our building of residual network, and we see there is other path from source to sink that contains edges that have capacities bigger than 0. Yep. So now we have this edge that make orange capacity. I mean that this color is equal to backward edge, and it means that we need to decrease flow through this edge, not to increase, to decrease. And we see that we can increase all flow by 1, but we need to increase flow through this edge by 1, decrease flow through this edge by 1, and increase flow through this edge by 1 too. So we get this picture. Yeah? We don't touch this edge and this edge. We decrease flow through this edge by 1 and get 0 flow, and we increase flow through these edges and get now 1 and 1. Yeah? Yep.
Why do we have 0 flow in the middle?
In the middle.
Yes.
Because here we have flow equal to 1. And we say if we have backward edges on the path, we need to decrease flow on the edge in the initial graph. And it is very important that to increase value of flow, we need to decrease flow on the current edge, and increase on the other edges. And now we have flow from flow that has a value equal to 2, and if we draw residual network, we see that there is no path from source to the sink. Do you see? Okay. And then we say that it is the maximal flow in the graph. Okay? And if we try to repeat these steps to this graph, we get 2000 steps, because one step increase our flow only by 1. And the maximum flow is equal to 2000. So we have 2000 steps of the algorithm. And it is bad, of course, because we want to get time complexity that depends only number of edges or vertices. Not does not depend to the capacities of it. Okay, and of course there is improvement of this algorithm, names as Edmonds-Karp algorithm, that that runs in this time. Okay, so if you want, you can Google it and find this algorithm too. It is equal, very similar to Ford-Fulkerson algorithm, but has a different understanding of what which the augmenting path we need to use in the residual network to increase our flow. Because we understand if we find this path in augmenting flow in the residual network, we increase our flow by 1000, then we increase by this path by 1000, and we have only 2 steps. It's better than 2000 steps, of course. So it's about Ford-Fulkerson algorithm, and some information about dualities. theorem that I write sometime before is equal to this theorem. Yeah. And it is one of the it is one of the duality theorems, and duality is an important method in optimization problems because, for example, in optimization, oh no. In the optimization, there are a lot of exercises to get infimum of the some functions, for example. And there is method to get quick lower bounds of this function, names as duality, and it is very important transformation that we can get primal primal problem, and to understand how we can bound this problem, we need to compute this number, and it is dual problem. And in some cases, it is simpler to compute dual task than primal task. And for example, in this case about flow and cut, about flows and cuts, we say that if we has a flow network and we want to understand what is the minimal cut of this flow network, we can get maximal flow, and then, as in this task, if we have maximal flow that goes through the graph, we say that we can get minimal cut, and it is true duality between two tasks. First, to find maximal flow, and second, to find minimal cut. And it is important to understand that we have this method, and maybe if we have time in the end of our course, we will talk about duality and other linear problems in the programming that we can solve with duality method. So that's all about today's topic. If you have any questions, you can ask, and you too. And if there is not any questions, we can end our lesson.
What is the minimum?
What is the minimal cut? Okay. We say that if we have flow network, we can put our graph into paths and say that cat is equal to value of the cat is equal to capacities that go from the left part to the right. For example, here we see not in the residual network. We need to get here. We see there are two edges, and sum of these edges equal to 2, and it is value of the cat, and we say that if we have flow network with maximal flow, then minimal cut of this network we can build by connectedness of a residual network. We say that from source we cannot reach any other vertices using edges with capacities bigger than 0. So we say that minimal cut of this network is equal to dividing set of vertices in these two paths. And for example, for the previous, we see if we get residual network from the source, we can go to A, because 5 minus 1 is equal to 4, and we have edge from S to A in the residual network that is that has capacity equal to 4 bigger than 0. And we see that 4 minus 2 is equal to 2, and we can go from source to the B using this edge in the residual network too. But in the residual network, this edge and this edge have capacities equal to 0. So we say that left part of this cat is equal to this subset of the vertices, and right part is equal to this subset of the vertices. And cut in the flow network, it is dividing set of the vertices into two parts. One part contains source and one part contains sink. And we say that it is minimal if it has minimal value. And value of the cut is equal to sum of the capacities capacities of the edge that start in the left part and end in the right part. Okay, we see that sum of these two capacities, if we sum it, we get 3. Yeah, and it's equal to flow that we have in this network. And of course we said that each cut and each flow has values such that value of the cut bigger than value of the flow. it's important that it's the theorem and very simple statement that for each law with value equal to f, and for each cut with value equal to c. We can say that f not bigger than c. It names as it names strongly duality, and it names as not strongly duality. I forget how to translate it. Weak duality, yeah. It is weak duality. So if we find such flow and such cut that it is equality, then we can say that such flow is the maximal flow in the graph, and such cut is the minimal cut of the graph. And for example, in this case, we say that we find minimal cuts because this value equal to 3 and value of this flow equal to 3 too. And then we say we get equality of this in this moment, and then we say that it is minimal and maximal cut and flow respectively. Understandable?
Yeah.
Okay. So it's about duality. I think we repeat it, of course, if we get the time to talk about duality in the end of our course.